Well, here's day 2 of Bronco's captivity. I haven't heard from his family yet. That's €1,000 to get him back alive. Otherwise, you'll never see him again. So what we're going to do is, this is the problem from the first problem on the old exam. And we're going to turn it into a system. Here's the trick. You do the following. You just say, okay, let, and this is a funny idea, let x equal y prime. That means x prime equals y double prime. And now we substitute and observe the following. I can take this equation and rewrite it as x prime plus 4x plus 3y equals 0, which means I can rewrite this as x prime equals negative 4x minus 3y. And don't forget, we had y prime equals x. Believe it or not, we have just done what we need to do. That's now a system. Let's look at the notation. Here's the key notation. We're going to let the vector xy stand for big Y with a vector notation. I'm sorry I'm using the same letter Y, but I'm using uppercase with an arrow to stand for a vector. So that means that this guy right here, this x prime, y prime, can be rewritten as big Y vector prime, and it's equal to the matrix negative 4, negative 3, 1, 0, vector xy, which is the same as saying it's the matrix negative 4 minus 3, 1, 0, y. And I'm going to tell you a deep truth, Bronco. In the olden days, you'll remember way back when we did problems like this, didn't we get y equals a e to the 5t? Didn't we get that? Now here's what's going to happen with this. With this system, when I have big Y prime vector equals this, we're going to be treating this as if it was a constant. But we don't have e to a matrix. E to a matrix power doesn't make sense. We don't have that concept. So what's going to happen is the solution will be big vector y is equal to constant 1. You're going to love this. E to the lambda 1 v1, where v1 is an eigenvector, and lambda 1 is the eigenvalue that goes with it from this matrix. And k2. E to the lambda 1t. E to the lambda 2t. v2. Honest to God, that's going to be the solution. I would like to show you why. Okay? How do we show something's a solution, Bronco? We just did that.
Check.
How do you check? I just said it. You take the derivative.
Right.
So let's take the derivative of this. Now remember, v1 is a constant. It's just a constant vector. v2 is a constant vector. So there's really only one variable up here. So this says that y prime vector is equal to the derivative of lambda 1t, which is lambda 1. That comes down, k1 lambda 1 e to the lambda 1t v1. The rest of these are all constants, plus k2 lambda 2 e to the lambda 2t v2. Well, that's the y prime side. We want the y prime side to be equal to that. So we'd like to do that matrix times y. So let me erase right here, get rid of all this stuff. What happens when you do a matrix times v1? What happens? So I'm checking this side. I want this side to be equal. We did this. We just did this for this y. We took its derivative. Now I have to do this side. I have to take this y times that matrix. So if I do negative 4, negative 3, 1, 0 times the original y, that thing times y, and that's k1 e to the lambda 1t v1 plus the other thing. I'm just going to let the other thing. This is going to stand for both, because here's what happens. I have a constant times a matrix. That's just a constant times a matrix. I have a scalar times a matrix. That's just a scalar times a matrix. This is K1 e to the lambda 1t times the matrix -4, -3, 1, 0 times V1. Well, V1 was an eigenvector, remember? So the matrix times the eigenvector is the eigenvalue times the eigenvector. And check it out. Here's K1, we got K1. Here's lambda 1, we got lambda 1. Here's e to the lambda 1t, we got e to the lambda 1t, and we got V1, we got V1. Same thing happens with lambda 2. That's why it solves. If you look at it in the big picture, this says on the left side you take the derivative according to the e to the lambda 1t rule. The derivative of the power comes down. And on the right hand side you have a matrix times an eigenvector. A matrix times an eigenvector gives you the eigenvalue times the eigenvector. So the two sides are equal but for a completely different reason. And that's what we're going to be playing with for the next month or so. It's a very rich method of solution and gets us through to do all sorts of really interesting problems. But this is the beginning of chapter 2. That's why we're going to be doing so much stuff with matrices and eigenvalues and eigenvectors. Because if you look at this, we didn't actually solve. We didn't get anything specific. I didn't get the eigenvalues and eigenvectors, but I could have. And I'd have a specific solution. And I can do these things all day. And where did it come from? Where did this system come from? You remember? I erased it.
Came from the original.
The first problem, and what was that? It was a second order linear. So we're actually solving vast families of second order linear differential equations just by turning them into simple little matrix things. That's what we're doing. It's really powerful. All right, you guys, that's the end of my videos for this week. Have a great time. See you later.